Having done materials mineral processing, that is the first step towards metal extraction either from pyrometallurgy or hydrometallurgical route. Now, we are in a position to go ahead with the various unit processes of metal extraction. Here first I will deal with the pyrometallurgical and then I will touch upon hydrometallurgical extraction unit processes also. Now, in this calcination is the first step and that is used for several purposes. So, here I am giving you first of all the material and heat balance problem in calcination, then I will proceed with little bit amount of concept and then straight away I will enter into the solution of these problems. So, the first problem, calculate the heat energy required to calcine 1000 kilogram limestone of composition 84% calcium carbonate, 8% MgCO3 and 8% H2O, which is charged at 298 Kelvin. Lime is discharged at 1173 Kelvin and gases leave at 473 Kelvin. Now, mind you, this limestone is not as used as such in various steel making processes or in non-ferrous metal extraction processes. As you will see in the solution of the problem, that the decomposition of limestone is associated with a large amount of absorption of energy. It is highly endothermic reaction. Therefore, use of lime requires that limestone should be calcined and therefore, this problem is included in order to appreciate you the fact that charging of lime after calcination of limestone is a very important step. That is the objective of this particular problem. Second, it is desired to produce 10 kg mole lime from calcination of calcium carbonate. Calcium carbonate is pure in a rotary kiln, while in the first problem it was only having 84% calcium carbonate, in the second it is 100% calcium carbonate. Rotary kiln is very often used to produce lime from calcination of limestone. The rotary kilns are very long kilns and they rotate 2 to 3 degree from the axis of the horizontal axis. From one side the feed enters and from other side the calcine material discharges. They are around 24 meter long these kilns and they are frequently heated by external source of energy and they are used for example oil or producer gas. So, this problem is concerned about that. So, you see that producer gas of composition, this CO2, O2, CO and nitrogen is combusted with 20% excess air to obtain the desired temperature in the kiln, because normally the temperature inside the kiln is very high and it may go at the order of 1500 degrees Celsius. The limestone and air are supplied at 298 Kelvin, whereas the producer gas is heated to 900 Kelvin, lime is discharged at 1200 Kelvin and gases at 500 Kelvin. Now, the fact that they are discharging at lower temperature than the kiln, there is occurring some sort of heat transfer before the product and the byproduct leave the rotary kiln. This is the problem number 2. Problem number 3, in the electrolysis anhydrous alumina is required. Now, the concept of anhydrous alumina is bauxite after leaching it gives you hydrous alumina, that is AlOH3. Now, as such electrolysis of AlOH3 is not possible because then only hydrogen will evolve. So, for that it is required that the Al2O3 which is used for electrolysis to produce aluminum, it should be anhydrous, in the sense there should be no water into the Al2O3 which you are going to charge in the Hall-Héroult cell. So, in the electrolysis anhydrous alumina is required. Now, for your information, in this anhydrous alumina the water is mostly chemically combined. So, it is not possible to remove the water just by heating by 100 or 200 degrees centigrade. You have to go to 12, 13 or even 1400 degrees Celsius to remove the chemically combined water from the product which you obtained after the Bayer's process. So, it is for this purpose a large amount of energy is required to produce an anhydrous alumina in order that alumina can be electrolyzed to produce aluminum. For this purpose, AlOH3 is calcined at 1700 Kelvin in a rotary kiln. A kiln receives a dam filter cake of AlOH3 analyzing this 55% Al2O3 and 45% total H2O free and combined, of which the proportion of combined water is very high, and produce pure Al2O3 as a solid product. The fuel consumption is estimated to be 0.2 kg of fuel oil of composition 84% carbon and 16% hydrogen per kg of alumina. You see, there is also required a source of energy, and therefore, the energy calculation is a very important step in almost all pyrometallurgical extractions. Say you are using around 0.2 kg per kg alumina, that is around 200 kg for 1 ton of alumina in order to have that anhydrous alumina. Assume complete combustion and heat losses 10% of heat input, 20% excess air is used for combustion. Now, you have to find out volume of gases, wet and dry composition, and perform the heat balance. Now, this is a very important step. Fourth, calculate the minimum amount of fuel to produce 1000 kg Al2O3, use the data given in problem 3. Now, here the whole idea is to know what is the minimum fuel. The minimum fuel is that fuel at which the heat input becomes equal to heat output. So, these are the problems that I have selected. Now, here some of the data you will be requiring to calculate the material and especially to calculate the heat balance. So, these are the data and these are the further data. Now, here what I have done, I have given you the heat content at the temperature at which the problem is there. That means, for example, calcium oxide is living at 1200 Kelvin. So, data are given according to that. However, I will request you that please try to calculate by using the Cp value of respective calcium oxide, CO2, N2O2 or whatever the product which are being discharged. That will give you an additional practice whether you can calculate the heat content from Cp value or not. This all requires a patience to see that you can do integration properly. However, this makes your life easier, but see that you do also with the by using the Cp calculation. Latent heat is also given, and here I have given some of the references. As usual, here I have given the solutions for these problems. Now, let us go for the solution of these problems. First of all, let me tell you what is calcination. First of all, let me tell what is calcination. In fact, calcination is also referred as calcining, also referred as calcining. It is a thermal treatment process applied to ores and other solid materials. Why? In order to bring thermal composition or rather thermal decomposition, because you want to decompose, for example, calcium carbonate to calcium oxide or CO2 or MgCO3 and so on. Second possibility could be phase transition, Third, removal of volatile fractions, These are some of the objectives of calcination. However, you can include more. Now, the temperature involved, they are say below the melting point, of the components of the raw material. That means, you treat them in the solid state. So, product is also solid. However, if the volatile component like CO2 or H2O, they will be leaving the system. Product of calcination product of calcination is sometimes called calcin. It is called calcin. Now, the furnaces which are used, they are called rotary kiln. Very commonly rotary kiln is employed. This rotary kiln is employed for production of cement. Cement industry rotary kiln has a very big application. Also calcination of limestone, also the removal of water from alumina and so on. Then fluidized bed reactors, fluidized bed reactors, multiple hearth furnaces, multiple hearth furnaces, and the fuel or fuel, let me put another, you can put source of energy. Source of energy, in some cases it is a fossil fuel, that is could be oil, natural gas, or there could be secondary fuel which are derived from fossil fuel, and normally sometimes producer gas is used, as you have seen in the problem, producer gas. Oil, the natural gas, all are the sources of energy. So, it is also an energy consuming unit process. Applications, some of the applications of calcination. One particular application is to produce cement Now, here the calcination is one of the important step where you get calcium oxide, and that is further mixed to produce a cement. So, in cement industry the decomposition of limestone is a very important unit process. Second application, decomposition of hydrated minerals. Decomposition of hydrated minerals. Hydrated minerals. Now, this decomposition is done for one purpose, could be we want to make say Al2O3 refractory. Al2O3 refractory. Now, here bauxite is the material to produce Al2O3 refractory. Now, bauxite also contains the water which is chemically combined. So, straight away you have to calcine it in order to produce an alumina which is free from water, and mind you, alumina is a very important refractory material in all pyrometallurgical extraction industry. So, one of the purpose could be produce alumina refractory, and another decomposition is for another purpose could be to produce alumina for electrolysis in Hall Héroult cell, as all of you know, because that Al2O3 should be anhydrous in the sense of anhydrous. Otherwise, there is a evolution of hydrogen, and you will be consuming a large amount of electrical energy to produce aluminum if you do not remove water from alumina. Third application could be decomposition of volatile matter, which is contained in petroleum coke, Another application could be heat treatment to affect phase transformation. However, in a strict sense you do not call it to be calcination, but since you are applying the heat below the melting point of the material. So, well you may class it under as a calcination, as a heat treatment, and you may not class it, that does not matter, but all that you require a solid state transformation from room temperature to another temperature. And so, these are the certain applications of the calcination. Now, having given those things, let us straight away go to the problem, to the solution of problem number 1. Now, problem number 1, you have to calculate the heat energy to calculate 1000 kg limestone, and composition everything is given to us. So, the reaction which takes place is CaCO3 solid, that is equal to CaO solid plus CO2 gas. This is the reaction, or this is the decomposition reaction. Now, we have 840 kg CaCO3. We are taking say 1000 kg limestone as the basis. Now, the basis is has already been given in the problem, 1000 kg limestone. So, 840 kg CaCO3, 80 kg MgCO3 and 80 kg water. And 80 kg water. So, this is all given to us. Now, we can straight away calculate the calcined product. The calcined product. Now, before that, what I have used? I have used the atomic weight of calcium as 40, carbon as 12, oxygen as 16, magnesium as 24. So, from here I will be getting calcium carbonate, the kg moles of calcium carbonate, that will be equal to straight away 8.4, kg moles of MgCO3, that will be equal to 0.952, and kg moles of water, that will be equal to 4.44 and 4. So, once you know this, now the calcium product immediately we can write down say calcium oxide and magnesium oxide. So, calcium oxide straight away say CS 1 kg mole, 1 kg mole and 1 kg mole. So, CaO will be 8.4 kg moles. MgO will be 0.952 kg moles. Similarly, the reaction for MgCO3 will be MgO plus CO2, that is all. So, we have the calcium product. Now, the gases that will form, because the gases will also form, na? So, we have to know the gases that will be forming the CO2. CO2 is coming because of the decomposition, and the sources of CO2 is CaCO3 and MgCO3. So, we have to add both of them, and H2O. These are the two sources. H2O is coming from the limestone composition. So, gases CO2 that will be equal to 9.352 kg moles, and H2O that will be equal to 4.444, they are in kg moles. Now, say we have to calculate heat energy. So, we have to calculate now heat of decomposition. Heat of decomposition. Now, the values I have given I will straight away write down the heat of decomposition, that will be equal to 382,186 kilocalorie. That is the heat of decomposition. Now, then I have to find out now sensible heat in products and gases. I have to find out now sensible heat in products and gases. That is all, that is what I have to find out, and from that, and if I sum total all this, that is what the energy I require if I want to decompose calcium carbonate. So, sensible heat for example, in CaO, that will be equal to 8.4 kg moles. Let me integrate it from 298 to 1173 Kelvin, 49.662 plus 4.519 into 10 to the power minus 3 T minus 6.945 into 10 to the power 5 upon T square. This I have to integrate to dt. Now, please do this exercise. However, if you try, you can get those values also in the reference which I have given, but then there are intermediate temperatures where you will not find the values. So, it is better to develop the practice of integration. So, if you do that, then the calcium oxide will be equal to heat content in calcium oxide 89547, that is kilocalorie. This is the heat content, or write method H 1173 minus H 298 in calcium oxide. That is what the value. Similarly, I can find out for MgO, that will be equal to now 0.952. Again I have to integrate from 298 to 1173, 48.995 plus 3.138 into 10 to the power minus 3 T minus 11.715 into 10 to the power 5 T square integrated dt. So, I get now H 1173 minus H 298 for MgO, that will be equal to 9542 kilocalorie. Then I have to calculate, let us say now the gases are discharging at 473 Kelvin. So, I have to just H 473 minus H 298 for CO2. The moles of CO2 are 9.352. I have to write its Cp value 298 to 473, 44.141 plus 9.037 into 10 to the power minus 3 T minus 8.535 into 10 to the power 5 upon T square to integrate it dt. So, that will be dt here. So, this value is coming 16,252 kilocalorie. Now, be careful while calculating the heat content in water vapor. So, we are starting 298 is our basis. So, first we will calculate H2O liquid 298, that is equal to H2O liquid 373 Kelvin, and this value is 6001 kilocalorie. Now, do not forget to add its latent heat of evaporation. So, another state is H2O liquid 373 Kelvin, that will be equal to H2O vapor at 373 Kelvin. All of you know at the latent heat temperature change does not occur. So, this value is 11158 kilocalorie. Now, I have to heat the H2O vapor 4.444, that will go from 373, because 100 Kelvin already has been taken into account, to 473, 30 plus 10.711 into 10 to the power minus 3 T minus 0.335 into 10 to the power 5 upon T square dt, and this value is 3643 kilocalorie. All that the heat energy required as asked in the problem, heat energy required, what would be heat energy required? I think by now all of you can guess. You have to sum total all the energies, because the heat of decomposition, that is also endothermic reaction. So, there will be large amount of heat absorption plus all the heat carried out. So, all that heat, if you do not supply, the decomposition of calcium carbonate will not occur. So, all that you have to add, and the addition brings 518,329 kilocalorie. Now, I have used 1 kilocalorie, that is equal to 4.186 kilojoule, and that gives me the 2.17 into 10 to the power 6 kilojoule, and that is the answer for problem number 1, and that is the way you will be proceeding to solve. Now, my appeal to you again, that please solve the problem on your own without seeing the solution, because if you look to the solution, you will be carried away by my way in which I have done. I would like you to develop your own ways and see that you come out with the innovative ways. I am sure that there will be definitely alternative way to solve the problem, and you, who knows that your way or your way of solution may be much better than what I have done. So, please do yourself, that is an important thing. Now, second problem, in the second problem you have to produce 10 kg mole of lime and so on. So, what we have to do? We have to calculate the amount of producer gas. Now, first thing, how will you calculate the amount of producer gas? Because producer gas amount is being asked. So, the only way to calculate the amount of producer gas is to do the heat balance. If you do the heat balance, because all the energy is coming from the combustion of producer gas. So, if you do heat input and make it equal to heat output, the only variable in your equation would be the amount of producer gas, and you can solve that way. So, heat balance is the key to solve problem number 2. Now, I will just make a box for you, so that I find it very convenient when I make a box and try to put all the values over here. It is not necessary that you also do in the same way. So, what I will do, what we are doing, say 10 kg mole of calcium carbonate, they are entering at 298 Kelvin, right. Now, it is fired with producer gas, and producer gas is entering at 900 Kelvin. Now, mind you, the producer gas brings sensible heat into the furnace, remember. So, the composition of producer gas is given CO2 it has oxygen, it has carbon monoxide, it has nitrogen. Now, CO2 is 7.2%, oxygen 1.6%, carbon monoxide 16.6% and nitrogen is 74.6%. Now, problem says further that air is 20% excess. That means, you use 120% theoretical air and the supply temperature of air is 298 Kelvin. That is what is given. Now, on the output side, your lime, which is 10 kg mole, and say lime is discharged at a temperature of 1200 Kelvin, and the gases, they discharge at 500 Kelvin. Now, the gases would contain, as you can see in the problem, it will contain CO2. Now, since excess air is used, it will also contain excess oxygen, and since air is used, it will also contain nitrogen. So, in this situation, you have to find out the amount of producer gas. Now, all that you have to do the heat balance. Now, here I will like to tell you that this is again, first of all, you have to make the material balance of this combustion. Now, for your information, I have also made one video course on fuel furnace and refractory, and there very detailed calculations on combustion in different lectures are given. The problems are also given to illustrate how to calculate. So, if you find any difficulty in calculating the amount of air which is required for the combustion, I will request you to see those video lectures on fuel furnace and technologies, they are also available. So, please, for the details you can see those lectures on combustion and you may get a feel how to calculate. I have also solved several problems over there. So, coming back to this problem, let us see that y kg mole is the required producer gas. Is the required producer gas. Now, first of all, we have to calculate the calorific value of producer gas. Now, the illustration of calorific value also I have given in the earlier course on fuel furnace and refractories. So, in fact, in case of combustion, the gaseous fuel combustion, the CO, hydrogen and hydrocarbon, they are the combustible component, CO2, N2, they are the diluents, they do not take part in the combustion. So, mind you, that is an important thing. So, the calorific value of producer gas that will consist of only when CO is completely combusted to CO2. So, the definition of calorific value is the amount of heat energy released when 1 kg or 1 meter cube of gas or solid fuel is burned completely, the products of combustion is complete, that is an important thing. For the detail you can see I already referred the video lectures on fuel furnace and refractories. So, the calorific value of producer gas, that would be equal to 11,271 kilocalorie into Y, because Y is the amount of kg mole of the producer gas that we have taken for combustion purposes. Now, straight away I can take the material balance now. Material balance. Now, if I do the material balance, then amount of CO2 that will be equal to 10 plus 0.238 Y. 10 is coming from 10 kg mole calcium carbonate will also give you 10 kg mole of carbon dioxide. Nitrogen all the nitrogen or producer gas will be available in the gases or the output, that plus the amount of air or the nitrogen of the air. So, that will be equal to 0.746 y plus 0.302 y. Then the excess oxygen, now remember here producer gas also contains oxygen. So, while calculating the amount of oxygen that is coming off air, you have to subtract the amount of oxygen that is already available in the system. So, that will be equal to 0.0134 y. So, once you have done material balance, now we have to do the heat input and heat output. Now, heat input, one is the sensible heat, heat of decomposition, though it is in endothermic, but it is also as a heat input. So, I will straight away write down the values. So, sensible heat in producer gas, sensible heat in producer gas that is equal to 4538 to y kilocalorie. Sensible heat in air is 0 because air is supplied at 298 Kelvin. So, I am not writing. Now, heat of decomposition of calcium carbonate, heat of decomposition, you have to calculate from the value CaCO3, CaO plus CO2 product mass reactor and so on, that I will already have illustrated in my thermochemistry lecture. So, that will be equal to 4,275,00 kilocalorie. Mind you, this is an endothermic reaction, this is not exothermic. Now, heat taken by calcium oxide, heat carried or taken by calcium oxide, because it is discharged at 1200 Kelvin, that is equal to 108,000 kilocalorie. Now, heat carried by flue gases, heat carried by flue gases, that will be equal to 19870 plus 1978.5 y. Now, all that you have to do the heat balance. Now, the heat balance would be say 4538 y plus 11271 y minus 427,500, that is equal to 108 plus 19870 plus 1978.5 y. So, I can calculate now y, that will be equal to 40.15 kg moles, and that will be equal to 899 meter cube expressed at 1 atmosphere and 273 Kelvin. So, that is equal to 2964 meter cube at 1 atmosphere and 900 Kelvin. So, this is all about problem number 2. Now, let us quickly go through problem number 3. In problem number 3, we have a rotary kiln. This is a rotary kiln. Now, in the rotary kiln, the flow is counter current. So, here wet cake, which contains 55% Al2O3, 45% H2O. Now, this H2O is, mind you, is chemically combined and it enters at 298 Kelvin. I always prefer to write all the details of the problem on this material balance figure. Now, the flue gases, they are living flue gases, they live at 800 Kelvin. Now, here fuel oil is supplied for combustion. So, fuel oil which contains 84% carbon and 16% hydrogen is supplied at 298 Kelvin. Here then supply 20% excess air, 20% excess air, or you can also call 120% theoretical air. This is also supplied at 298 Kelvin. Then you have calcine, alumina, which is at 1000 Kelvin. So, that is what is given to us. Now, as usual, we have to perform the heat balance. Well, first of all, you have to do the material balance, without that you can do nothing. So, I will just proceed to solution. Now, here, well, let me tell another thing here. The wet cake, it goes in this direction, which is the direction of flow of wet cake, and this is the direction of flow of flue gases. That is how the flue gases are living. So, they are in counter current mode. So, the basis of calculation is 1000 kg calcine Al2O3. Now, amount of fuel oil 200 kg is already given. Now, the various calcination reactions is 2 aluminum OH3, that is equal to Al2O3 plus 3H2O. This is the calcination reaction. Then we have combustion reaction, and combustion reaction is C plus half O2, that is equal to CO2. Now, remember, if nothing is given, then always assume there is a complete combustion, and the product of complete combustion are very clear. Carbon is CO2, H is H2. So, 2H plus half O2, that is equal to H2O. So, we have assumed complete combustion. It is the complete combustion. So, let us now calculate volume of H2O in flue gas, that will comprise of volume of hydrogen, that is combustible to H2O, plus the water which is removed from the cake. So, that will be equal to 1376.4 meter cube. Similarly, we have CO2 in the flue gas, that will be 314 meter cube. Then since we are using 20% excess oxygen, so there will also be excess oxygen. So, excess oxygen in the flue gas, that will be equal to 98.6 meter cube, and nitrogen in the flue gas, that will be equal to 2225 meter cube. Now, I may tell you once again over here that it is utmost important that you should be very thorough in doing material balance, because without material balance you cannot do heat balance at all. If you have any problem you have done while doing the material balance, that this problem will be carried over till the end of the heat balance, because you have to multiply all the values of the amount with the heat that is being produced. So, if you do a mistake in material balance and if you get a solution say after having 10-14 steps, then all steps will be wrong. So, it is a transferred error. So, you have to be very careful while doing material balance problem, that is very important. So, here we have to calculate volume of flue gas. So, immediately we can calculate volume of flue gas. We have to calculate wet and dry. So, wet volume is 4014 meter cube. Now, then you have to calculate composition. The composition wet basis, and you have to also calculate composition on dry basis. Composition dry basis. So, we have CO2, we have O2, we have nitrogen and we have H2O. So, if you do this calculation, as I already given in the answer, 7.8%, 2.5%, 55.4% and 34.3%. Now, these volumes are all on volume percent. Dry, that will be 11.9%, 3.7% and 84.4%. Mind you, also all these volumes, they are expressed at 1 atmosphere and 273 Kelvin, because I have taken 1 kg mole is 22.4 meter cube. So, that is what this calculation of the composition. So, heat balance we have to do it. Heat balance, all that we have to do heat input, say heat input 1 will be by combustion. So, you have to calculate C plus O2 CO2 and H2 plus half O2 H2O. So, this heat input by combustion, that will be equal to 241,4120 kilocalorie. Then heat of decomposition, heat of decomposition of calcium carbonate, because this is an endothermic. So, if I do combustion as positive, then this will be equal to negative 238,137. This is the heat input. Now, heat output that will also be in kilocalorie. Flue gases, that will be equal to 136,2135. Then Al2O3, it is being discharged at 1000 Kelvin, it will be 183,431. Then heat losses are given as 10% of the input. So, here the input will be 217,593. So, heat losses will be 10% of that, 217,598. Then we will be having surplus, that will be 412,819. So, if we sum total all, it will again be equal to 2175983. So, that is how you will be doing the heat balance for the problem number 3. Now, quickly illustrating the problem number 4. Now, in problem number 4, all that you have to find out the minimum amount of fuel for calcination in problem number 3. Now, as you noted in problem number 3 that there is an excess amount of heat and all the amount of heat is coming from combustion of fuel. So, that means the minimum amount of fuel will that fuel at which the heat input becomes equal to heat output, and that value will be your amount of fuel that is required. So, again you have to do the heat balance. So, just if I say if you have x kg fuel, so from here you have to start, that is unknown. So, x kg fuel, your carbon will be 0.84 x, hydrogen will be 0.16 x. So, the products of combustion, that will be equal to 0.07 x, that is CO2, and 0.08 x H2O. Mind you, they are in kg moles. This is in kg. So, once you know the products of combustion, then you have to calculate the amount of flue gas. So, the flue gas composition, flue gas CO2, that is equal to 0.07 x, H2O 0.08 x plus 45.45, oxygen 0.022 x, and nitrogen, that is equal to 0.496 x. Now, one had to do the again heat balance, heat input, heat output. So, well, this heat input and heat output I already done in problem number 3. So, if you balance both, then the only unknown will be x, and this x will come out to be equal to 144.4 kg. Now, prior to that you have to perform heat balance, and in heat balance you will be including the term like heat of decomposition, heat taken by flue gas. Now, heat taken by flue gas will be in terms of x, then heat taken by Al2O3. So, if you do all that and you do the balancing, then the answer will be 144.4 kg, and that is what about the calcination.